So you can just download it and read the details. And I will just go through this chapter, okay, about reliability and the validity. Let's just look at the validity first. These two concepts are extremely important in measurement, okay, or in stats. And when you submit a grant or when you write a measurement paper, so you have to report the validity and the reliability, something like that. Okay, so let's just have a review. We mentioned the measurement model last semester. Okay, so we assume that each observed Y here, it's not the true score. What we want to measure, actually this T, the true score here, but because this is a not perfect world, so we cannot get the score of the true score, the true latent trait directly. So we have to use some tool or some measurement tool to get that true score. So we have the measurement error here. Combining the true score, it's unknown, and the measurement error, and we have the observed Y. Okay, Y has some part, Y has some part of E, which is due to the error. And of course, we have assumption for this CTT. This is called the CTT, okay, classical test theory. So the mean of this error is 0. So okay, this is assumption, and also E and the T, these two, the true score and the measurement errors are uncorrelated, are irrelevant. Okay, so we have two assumptions. Then we're gonna look at two very important concepts here, validity and the reliability. Okay. So validity, we're gonna look at different types of validity. So how to get that measured? So we have different methods to measure that. And we're gonna look at examples to measure the validity. We're gonna use a MTMM table. So what is that? It's multi-trait, multi-method matrix. So basically, we're trying to measure some traits together by using different methods. And then by looking at their correlations, okay, we're gonna figure out what is the detailed types of validities, for example, convergent validity or discriminant validities. We will just look at those concepts next. And these are our documents. Okay, so now we'll see. So what's the definition? Validity deals with whether a variable measures what is supposed to measure. For example, if you want to try to measure people's IQ, okay, how smart is that person? But we don't know. We use some questionnaire or we use some test to get, okay, so is that person get a really high score or low score? So we're trying to look at the variable. Okay, so we designed a test. That test is valid or not to measure the IQ value of that person. Okay, so when you look at the definition, you know that you immediately know that the validity study is empirical kind of research. It's not very statistical way to define it. First, okay, what is supposed to measure? So it's very vague. You have to give a definition of something you want to measure, and then you're trying to measure the validity. So it's kind of like an empirical piece of research, okay? And the people trying to use 3 types of methods to measure the validity, which are content-related, criteria-related, construct-related. So what are these? Okay, what are these? First, let's look at the content-related. This is the most difficult validity, actually, because it's also very hard to define a concept. Okay. So if you want to try to use this validity, you have to have a very well-defined concept or something you're trying to measure, and then you base on some rules, predefined rules, and you judge if a measure is measuring a domain. Okay, so it's always difficult. It's qualitative. Okay. It cannot be evaluated empirically. So move on. Okay, it's just very vague definition. Then people try to make it more detailed. We can use some criteria. Okay, it's called the criteria related validity. So first, we have to have some criteria, existing criteria. And then we try to get some measure and try to get the, actually it's kind of like correlation between these two. Okay? So we have two types of criterion related validity. One actually is concurrent validity. The other one is predictive. So for these two, actually these two are quite, these happened quite at the same time, but these you can have the previous and the predict in future. Okay, we have different time points. So for example, self-report and clinical diagnosed depression, you can do this both at the same time. Okay, self-report and the clinical diagnosed depression. And also you can have salary and the job, okay, to measure, okay, by using the salary to measure what's the contribution, okay, so of your job, something like that, okay. Although it's not very accurate, I know, okay. And the predictive validity, for example, the SAT score and the college GPA. So it's kind of like a predictive. You can use SAT to predict the future's college GPA. Or by using the index of leading economic indicators to predict some kind of like a GNP, okay, gross national product. So again, yeah, so this validity is kind of like a better than the previous content related, but still it's not quite clear. So let's look at the example. So here we have the true score here. This is C1 is the true score we're trying to measure. What are the true score? We have the measure 1 here, okay? This is our observed score. But we do have a criterion here, C1 here. C1 actually is another measure here, but this is existing, okay, system. And both of these, okay, X1 and C1 actually is a function of the latent variable C. So you have some weight here. So this one is kind of like the weight here times the true score C and the measurement error part here. C1 is the lambda one, the weight times the true score C1 here and plus the measurement here. So if you go to the page 187, so let's check the textbook 187 here. Okay, so this is a model I just described here. We have X measure here, criterion C here, and the function. Both of them are function of latent variable C. So you can see that X1. Let me make it larger. Okay, so X1 is the weight lambda 1 here times the latent score C1 plus in the textbook they use delta, but here in the slide we use Z. Okay, it's just notation. It's the same thing. So we have some part of the measurement error here. So this is X1, and also we have C1, it's a criterion, and we have a function like this. And we just do the correlation, okay? So here we have the correlation, okay, between X1 and the C1, X1 and the C1 here. So just by just following the rules we described in the measurement model, we have the coefficients here. We have phi11. Phi11 actually is a variance of C1, okay, it's a variance of the true score here. And then the variance of both parts, and take the square root. So this is a standard deviation of X1, and also this is standard deviation of C1. Yeah, question?
Yes, ma'am. So on the homework, you asked about us to explain validity, reliability differences. How in depth do you want us to give? Because you're like on your examples.
You don't need to cover these examples. Yeah, you do have homework 1 about validity and reliability, and the requirement is okay.
And difference.
For example, validity, you need to describe the definition, types. Okay, we have different types, and related methods. Okay, and limitations. So you don't need to cover
Don't
the
go this
detail.
and
No,
that. Okay,
it just help you how to understand the criteria related
Sure.
to validity. It's just
Sure.
one type of validity. Yeah,
okay, I didn't mean to interrupt. I was just want to see
That's a good
how
question.
far deep you want us to go.
exactly. Yeah, it's that,
Okay.
exactly. Yeah, thank you. Yeah.
Okay,
So actually, just correlation between these two measures, and based on the formula or rules, we can have this equation. Okay. And that's a second type. So we also have construct related validity. So this type is more detailed than the second type. Okay. So we have two sub validities in this main branch. We call convergent validity and the discriminant validity. We have two subtypes. So this type of validity assesses whether a measure related to other observed variables in a way that is consistent with theoretically derived predictions. So we have some other measures, and we just look at the correlations to see, okay, if that is consistent with the theoretically derived prediction. So how are we going to understand this sentence? Okay, so let's look at the example here. Again, so here we have two measures, x1 and x2. And these are two scores, okay, C1 and C2. We have, of course, we have the weight or coefficient here. And we have the measurement part here. So we're trying to get the correlation between these two and to see if this correlation is small or large, to see if it's convergent, if there's a convergent validity or discriminant validity. Let me show you what the details of this. Okay. So we have two types for construct related validity. What is convergent? Convergent. Okay. It's kind of like a similar part. Okay. It measures. These are measures of construct that theoretically should be related to each other, are in fact observed to be related to each other. So theoretically, two measures should be highly correlated. We should have very high correlation. And what we observed, it is still true. Okay, then in that case, we think that there's a convergent validity. It's quite true because theoretically, these two correlations, okay, these two measures are highly correlated. And then what we observe, it is in fact highly correlated. In that case, we call that, okay, there is a convergent validity. The other part, okay, it's called a discriminant validity. It's opposite, okay? These are measures of construct that theoretically should not be related to each other, are in fact observed to not be related to each other. So discriminant, okay? So two measures should have really low correlation because they are independent or they are not highly correlated. And what we observed, it is that case that we call that there's a discriminant validity. Again, it's quite abstract. Okay, it's just verbally discrimination, verbally definition of these two validities. Let's try to use a table. It's called MTMM table to apply those concepts to this example. Okay. So this is table. Okay, it's called multi-trait, multi-method. So we're trying to collect the data on multiple traits and by using multiple methods. Okay. And by using this table, we look at the convergent and the discriminant validity. And also we have the paper uploaded. Okay, so let's look at the matrix. This is a table. Actually, this is a correlation table. It's just a correlation table. But we have different columns, different rows to show different traits and different methods. So both of these, okay, convergent, either convergent or discriminant, This belongs to construct related validity. Okay. So this is a table from our textbook, okay, page 191. This is the first example. We have two methods, method 1, method 2. Okay, method 1, method 2. For each method, we have two traits, okay, x1, x2, x1, x2. So x1 and x3 measure the same trait by using different method, method 1, method 2. Okay, so we have 4 measures, 1, 2, 3, 4. So we have 1, 2, 3, 4. We have correlation table here. Okay, so the diagonal part is 1, 1, 1, 1. So this is x1 correlation here, and here this is a correlation between x1 and x2 here, and this is a correlation between x1 and x3. This is a correlation between x1 and x4. It's just correlation table.
Yeah. The square you said is it observed or because last semester you mentioned squares and circles, meaning observed
okay.
or
Here just emphasize this part.
Okay.
It's not a related
Okay.
test diagram. Yeah.
Okay.
Good question. Yeah. We just emphasize this part. Okay, because this actually tells us what? This is a correlation between x3 and x1. These are the same trait, but these are measured by different methods. So we hope, we expect this value high, because theoretically, this correlation should be high. If we observed this value is high, then we can say, okay, there's a convergent validity. That's how we use the MTMN. It's quite simple. Same thing here. X4, X2, they are measuring the same trait by using different method, okay? Method 2 and method 1. So this value theoretically should be high. If we observe, okay, what we observed the correlation here, if this in this space, what we observed, correlation is high, then we can say that okay, there is convergent validity, something like that, but not these scores, okay? So what is this correlation? This is a correlation between x1 and x2. They are different traits. For example, math ability, verbal ability, different traits. Although they using the same method, for example, computer-based questionnaire or paper pencil based. Although they use the same method, but this is a correlation between two traits, different traits. So theoretically, this value should be low. If we observe this value, okay, it is low, then we can see, okay, there is a discriminant validity. Okay, that's it. That's it. And same thing here. This is a correlation between 1 and 4. Okay, different methods, different traits. So this value should be the lowest among these. Okay, different traits, different methods. So if it is low, then we can see there's a discriminant validity. This one, okay, different methods. Yeah, same thing. Okay, different method 1, method 2, and the different traits. Also, this one should be low. This one, different trait. Although the same method, okay, method 2, same method, but they are measuring the different trait, x3 and x4. So it should be low. So what does that mean? So if you want to check convergent validity, you need to check the row 1, 3, and row 2, 4. Okay, here. 1, 3, and 2, 4. So these values in the box. Okay, so these two should be high. Then we can say that there's a convergent validity. Discriminant validity. So that value, those two values should be higher than the remaining, the rest of the correlations. Okay, so these two values should be higher, all of these, okay? And actually these two should be the lowest numbers among these 6, okay? Again, this is kind of like a very rough, okay, estimate of validity. That's how we said that validity is not, it's empirical piece of research. It's not very statistical defined. Wait, okay. Okay, in this example, we only have, okay, 2 methods, 2 traits, 4 by 4. Let's make this a little bit complicated. We have a second example. This is an example also from our textbook. Okay, we have 3 methods. Method 1, 2, 3. For each method, we have 3 traits. Okay, A1, B1, A, B, C. Okay, A, B, C are 3 traits. These are measured by the first method. These are measured by the second method. These 3 are measured by the third method. Okay, so actually it defined. Let's look at the which page. Yeah, convergent and discriminant validity. And this is the table we just discussed. And here, that's it. Okay, that's it. This is a tip. No, this is another example. Here we have 4 traits. Okay, so this is let me see. This is another example. Here we only have three traits, 3 methods. Okay, just look at this example first, and then we can change the 3 by 4 table. So here I'm gonna show you different concepts. In this table, or those one correlation table, there are a lot of concepts. So mono method blocks, okay, reliability diagonals, okay, hetero method blocks. So how to look at those concepts? It is not a correlation table. Actually, there's a difference between this table and this previous table. Here, in the diagonal part, we do not have 1, 1, 1, 1. In the correlation table, just 1, 1, 1. But here, we replace those 1, 1, 1, 1 with the reliability. Actually, these are reliabilities. Okay, we're gonna cover the reliability next session. But remember, those are reliabilities. Okay, this is from the same method, the same trait. It's not 1. Actually, we replace the number 1 with these reliabilities. So I just simplified that table here. Let's look at these 3 blocks. These are called mono method blocks. Okay, why? Because all of these, okay, from the same method. Method 3, correlation. Okay, this block actually is the correlation from method 3. Okay, this block actually is the correlation of the observed variables from method 2. This is from method 1. So these are called mono method blocks. And these 3 blocks are called hetero method blocks because this is a correlation among method 1 and 2. Okay, this is between 1 and 3. This is method 2 and 3. So different methods, hetero method blocks. And then the diagonal part, okay, as I mentioned, these are reliabilities, okay, estimated reliabilities. So among all of these numbers should be the highest or the largest numbers, okay, because it's reliability. It's measures, it's among the same trait by using the same method, okay. So this number should always be the largest among these numbers, okay. Reliabilities. So yeah, let's just look at the detailed definition. Okay. We have monotrait, hetero. So this is these are different concepts. This is also monotrait, hetero method correlations. Okay, so these are, let me see, validity. So these are called, these also diagonals. Okay, these are called validity diagonals. It's convergent. So let's look at those blue fonts, those blue numbers. These are, for example, here, this is the correlation between the same trait A, but different method. So trait A but from method 1, method 2. So this is convergent validity. Of course, we call it diagonal because all of these form are diagonal. So all of these are convergent validities. Okay. So this number and this number tell us the correlation between the same trait B, B1, B2, method 1, method 2. This is the same trait C, method 1, method 2. And we also have these three numbers, Okay, this is a correlation between method trait A by method 1 and method 3. Okay, trait B, trait C, method 1, method 3. This is the correlation between A, okay, that's the 2 and 3 here, 2 and 3, 2 and 3. So these are convergent validity diagonals. So by comparing the reliability diagonals, okay, with this one, so you can see that these are always the largest one. This should be the second largest numbers, okay. This is second group. They should have high numbers because it measures a convergent validity. So theoretically, these numbers should have very high correlation because they are measuring the same trait, although they use different method. Okay, this is the second group of numbers. So it should be high. Okay, so it's called mono-trait hetero method. Okay, it's the same trait. A different method correlations with validity. Yeah, so the same trait, the different methods, and yeah, so we just explained these numbers. Okay. Because the two measures are of the same trait or the same concept, so we expect, okay, so theoretically, we expect them to be strongly correlated. Okay, let's look at the other part. It's called mono-method hetero-trait triangles. So here we have some triangles. It's from the same method, okay? Same method, but different trait. This is the correlation between A and B. This is the correlation between A and C. This is the correlation between B and C. Okay? All of these are measured different traits, okay, although they use the same method. So these are called mono-method hetero-trait triangles. They share the same method. Okay. And let's look at the other triangles. These are called hetero-method hetero-trait triangles. Okay, all of these, okay. So let's look at these numbers. This is the correlation between trait B and trait A by using different methods, method 2 and method 1. So we expect these numbers are quite low because these are correlations between different traits by using different methods. Okay, so these numbers should be the lowest in the whole matrix table. Okay. Yeah, so this is a review for the discriminant validity. So theoretically, they should not be related to each other and are observed to not be related to each other. So these just tell us these numbers, okay, should be low. So if we have a table with really low numbers, here we can say that there's a discriminant, there's a discriminant validity. That's it. Okay, so we just give a very short explanation of this table. So basically, we have different concepts. Okay, blocks, diagonals, triangles. If we have really good measures, so we expect the reliability diagonals have the largest numbers, and then we should have the validity diagonals. These are convergent validity diagonals. These numbers should be high, but not as high as reliability. And then we should have kind of like a medium size of the red part. These are hetero-trait mono-method triangles. And finally, we have this part, okay, hetero-trait and hetero-method triangles. We have different groups. So if we go to the book chapter, actually, this is a more detailed example. So it's called still the multi-trait multi-method correlation table. And we have three methods. Okay, self-rating, peer ratings, observer ratings. We have three methods to measure what? To measure a person's, four traits. Prominence, X1, or X1 here. And then achievement, X2. Affiliation, X3, leadership, leader. We have four traits for each person. And those scores can be collected by self-rating, peer ratings, or observer ratings. So we have this huge, 12 by 12. Here we have four traits, three methods, 12 by 12 correlation table. And in this table, there's no reliability. They still use a correlation table. They use a 1-1-1 in the diagonal part. Because the reliability is not available in this table, so they just use a 1-1, but it doesn't matter. So that's that's a validity part. It's quite simple. And also, again, as I mentioned, it's kind of like an empirical piece of research. So we just use some content or criteria or constructed to define those validities. We have a summary here. So validity deals with whether a variable measures what it is supposed to measure. And we have three types. In your homework, you can just describe, the first part, and also three types. We have three types. In the third type, the third type of validity, we also have two subtypes, convergent and discriminant. And you can just talk about these definitions, descriptions. So you can just check the book chapter here. Yeah, you don't need to cover all of these examples because that's too much. But show me your understanding of this validity, because in your future, in your research, you're gonna see those. You're gonna report some of these validities. This is one part of our chapter 6. Question for validity. Actually, there's some other specific form to define those validity. For example, people use AVE, something like that. So there's some other detailed forms. But in general, that's it. This is the validity part.
So is this the statistical or the MTMM, the statistical way?
It's a very rough way. When we learn the factor analysis, so we're gonna cover factor analysis. We're gonna use another method, statistical method, to go back this topic again. So this is a very traditional way or vague. It's a very vague method to try to look at the convergent validity and the discriminant validity. When we have factor model available, we're gonna truly check those factors, and then by looking at those examples again, we will come back to this chapter again. So that is more strict way. That is more specific way to look at the validity. Any question? Then let's have reliability. We can talk about reliability a little bit, then we can have a break, and then we continue that topic. So we just covered this part. We have example of MTMM. Now let's move forward to reliability. So let's look at the concept. So what are we going to do by using reliability? So we want to make sure how much of the variance of the observed score is due to the variance of the true score, the latent true score versus the variance of error. So we have two parts, okay, based on the CTT. We have true score part, we have error part. So we're gonna try to look at the variance of the true score versus the variance of error. So we're gonna do some comparison to figure out what's the proportion of the variance of the total scores coming from the true score. So mathematically, we have this formula. So it's just a ratio. It's a ratio. The top part is the variance of the true score. P means true score. Bottom part, it's a sum of two variance. Actually, this is a variance of the observed score because we have assumption in the CTT. The true score and the error are independent. So the variance of the raw score, the observed score, is a sum, direct sum of the variance of true score and the variance of the error. Okay. If they are not independent, there's a covariance. Then we also need to look at the covariance. But by using our assumption, the covariance is actually zero. We don't have the correlation among them. So we just simply the sum of these two parts. This is a variance of the raw score or the observed score. This is the variance of the true score. So we're trying to look at the ratio to figure out what proportion, okay, how much the variance of the observed score is due to the true score. So of course, this part is, if this ratio is bigger, then this part is bigger, then it's better. Okay, so we got the most part of the variance coming from true score, which is good. Okay, but sometimes it's not practical, so we need to check the reliability. Okay. That is a definition. It's widely used in all measurement or in grades. Okay, so if you have different tests, test A, test C, so you're gonna check the reliability. Okay, or questionnaire. Okay, great. Or yeah, we widely use the concept, experimental tests or measurement procedures. And again, we're gonna check the look at the chapter 6. Okay, about reliability. So basically, we have 3 types of measures in CTT. We start from CTT. Again, we start from the classical test theory. So let's look at this chapter. So it's better to use a chapter here. Okay. Reliability. Okay. Of course, okay, reliability and validity are different. Okay, reliability is the consistency of measurement. It's not the same as validity, since we can have consistent but invalid measures. Let me just show you this plot first. This is extremely important to show the relationships among these two concepts. So suppose this is our target, okay? So we try to measure this concept. This is our target. If you have this observed variable, it's called reliable but not valid. What does that mean? So we try to measure this thing, but actually we missed the target. What do we measure? It's here. But let's look at a bunch of observed variables. They are very close to each other. Every time we measure this part, it's around this area. It's very reliable. It's always here. Okay, it's very reliable, but it's not valid. It's not valid because our goal is here, but we missed the target. We measure something here. But for the question or for your measurement tool, it's very reliable. Every time you got some score in this area. In this case, it's valid, but not reliable. We try to measure something here. It's good. Okay, we cover some error here, but it's not reliable because every time we have some very dispersed answers, it's not the answer is not kind of reliable. Okay, so sometimes we got here, sometimes we got there. Okay, it's not quite reliable. In this case, neither reliable nor valid. Okay, we mainly measure something above the target. Okay, and also it's not concentrated, so it's not reliable, not valid. This is the best case, both reliable and valid. Okay, this is our target. We measure something here and it's very reliable. Okay. So this is the best case. This is the worst case. Okay. And actually those are all not good cases. What we want actually is the first case, but in reality, it's quite hard for us to get the first case. So that's why we have two concepts, okay, reliability and validity. Okay, so let's go back to yeah, so let's go back to the slides. Yeah, it's not the same. Okay, reliability is not the same as validity. Because, okay, we can have consistent, okay, consistent means that reliable measures, but invalid. Just like the case here. Consistent, okay, but invalid measure. And it also gave us some examples. Okay. So the detailed examples here. Yeah, so the distinction between reliability and validity is important. And for homework 1, I also asked you the differences or the relationship among these two. And for reliability, you also needed to answer the definition, the types, okay, the methods, okay, limitations, advantage, something like that. Yeah, we will cover this part. So let's start from the measurement part here. So here we have 3 types of measures, okay, parallel, tau equivalent, and the generic measures. So what are these? Okay, so we have this is very, let me just close this one.
So may I add something?
Yes.
Maybe you can think that validity is about the latent variable which you measure your test or scale, but reliability is about your scores.
Yes.
There is test scores or scale scores, and so you have to report your reliability according to your results. So they are really different.
Yeah.
I just want to.
Yeah. It's a good example. Yeah. Just yes.
My
Say more. Yeah.
good, so I can't explain everything. But
Yes, you're right. Yeah.
Okay.
Yes. Yeah. Okay, so we have 3 types of observed variables. Okay, called parallel measures, tau equivalent measures, and generic measures. What are these concepts? Okay, so here we have the detailed definition. Suppose, okay, this is observed Y. Okay, this is a true score, and assume we have some loading or coefficient or weight here, and we have the measurement part here. And we have another measure, okay. This is xi, this is x3. So when we see these two are parallel, what does that mean? Parallel, it's almost the same, okay, it's parallel. So we're gonna make sure all of these are the same. So let's look at the conditions, okay, so assume that the true score are the same, okay. The true score at I, true score at J, tau I and tau J, I mean, don't move the cursor here. These two are exactly the same. And if alpha J and alpha I and alpha J equal 1, okay, so this coefficient, because CTT, if you look at the CTT, the coefficient fixed, okay, fixed at 1, fixed at 1. These two are 1s. And the variance of the residual part or the measurement error part, variance of EI equal to variance of EJ. In that case, these two measures are really close to each other. They have the same coefficient 1 here. The true score is here. The variance of the EI and EJ is the same. In that case, we call these two measures parallel. In reality, it's not easy to get the parallel analysis, parallel measures, because it's very, it put a lot of assumptions on these concepts, okay? E and EJ could be different because they are different measurement areas, but we assume the variance, okay, the variance of EI and the variance of EJ is the same, and then T is the same, alpha the same. And then in that case, it's parallel measures. Let's relax the assumption a little bit. Alpha I and alpha J still it's 1, okay, equal 1, but these variance, okay, variance of EI and variance EJ are different. The measurement part, we can relax the measurement part. The variance EI and EJ are not equal to each other. Then those measures are called tau equivalent. Why it's called tau equivalent? Tau is just this tau. This is tau. Tau equivalent. So the tau part, the true value part is equivalent, but the measurement error part are not equivalent. So that's how the name comes from. Okay, tau equivalent. The true part, we have the alpha 1, alpha j, 1, 1, and the tau, the tau I and tau j is the same thing. But the variance of the measurement part is different. So that's tau equivalent. Let's try to relax that assumption again. So if alpha does not equal alpha j, and also variance of E and EJ are not equal to each other, these are called congeneric measures. So xi and xj may measure different scales of the true score. So the alpha I may equal 1, okay, alpha j may be 2. So they have different scales. In that case, the xj actually is the twice of the true score. But for xi is the 1 scale of the 2. It's kind of like different measures. But still, we have the true score the same. In that case, we call it, okay, congeneric measures. Okay, so three concepts. So congeneric measures are the most general case. In our real life, maybe we have just congeneric measures. So parallel measures are very, very strict. Okay. So these are 3 types. Okay. So this is the 3 types of CTT. And then reliability are based on these different types. We can have different forms. Okay. So yeah, we have different definition for these different parts. Let's have a break. So now it's 6:15. So we can have a 15-minute break, and then we're gonna go to the details of that part. And then we will look at Cronbach's alpha. It seems that everyone uses Cronbach's alpha, but do you know why do we have that formula? What is the formula first? What is the formula? Of course, you can use software and report that number, but how do you get that number? What is the formula? Second, how do we get that formula? How do we derive from that formula? So we will cover that part in detail in the next session. Okay, so, and also actually, you know what, the Cronbach alpha is not good measure of reliability. It's just give a lower bound of the reliability. If you have SEM or especially effect models already, there's another advanced method to measure the reliability. It's called the structural SEM factor part of the. So what are these? So that's for the next session. Okay. Yeah, we can have a 15-minute break. think it's all good.
Yeah.
Oh, I'm sorry.
It's so
Yeah,
hard.
yeah,
It's
yeah.
so hard.
I add you to the. Oh, you still have the no ID.
ID.
You have ID?
Yes.
Well, then I
No,
think-
you can't.
I think that you have ID, then I can. Yeah, so.
Want to tell you something that would change the way you look at this word? That's not. I want to like.
Still working on the word.
I am. I'm like, this is like the minimal of the it's like cute, like I have 70 consonants that I'm gonna figure out. And then and I have to hear it, letters. It's just like I'm better at scrambling it, right?
I mean, that's what you do on a farm.
Good, okay, thank you.
Come on, you know me, just tell me to shut up.
Okay, let's look at the reliability again. Sorry. Oh, yeah. So we have three types of measures, and what's the reliability form for each of them? Okay, so go back to the chapter here. So these are forms of the these measures, okay, Xi and Xj. So for tau equivalent or parallel measures, so tau equivalent, that means tau part is the same, but the variance part is not the same. For parallel measurement, the tau part and the measurement, the variance part are exactly the same. So we have this reliability. So actually you can just get it by yourself, whether based on the formula, we can, so X is alpha, we use tau plus B here. So of course we can use I here, I here. So we try to get the variance of this is a true value, okay? This is the true value. So the variance of this part, this alpha tau is alpha squared, because think about the definition of variance. Okay, variance. The variance, we have alpha squared here, and then variance of the tau part here. Okay. So this is the true part. This is the top part. The top part here. Okay. So this is the top. And then we have the raw score. This is the raw score. This is the variance of the raw score. So the ratio is just our variability. So when it's tau equivalent in the parallel measures, remember that the conditions for tau equivalent in the parallel measures, the alpha is 1. So when alpha is 1, then it becomes a variance of the tau over the variance of x. So that's it. But for congeneric form, when tau is not 1, then we can just use the original alpha here. Okay. So it's very natural. So got the form. And then let's look at very important statement. Let's look at this, the relationship between the reliability and the correlation. Okay, so reliability is the ratio of the true scores variance. Yeah, this is the definition. The true scores variance to the observed scores variance. It equals, okay, reliability equals the squared correlation of what? Observed score and the true score. So this is a very important statement for reliability. So if you know the correlation between the observed score and the true score squared, that is our reliability. How? Yeah, this is a proof. Okay, so let's try to look at this is the definition of reliability. I'm sorry, correlation. This is the definition of the correlation between X observed variable here, tau is a true score here. Okay. It's too high. Okay. So we have the observed score X here. Tau is a true score. Try to get the correlation between these two, and then squared. Let's try to prove that this is our reliability. So again, based on our definition of the correlation, So we have the definition, okay. Covariance between x and the tau, choose observer score, choose score here. Variance of x, variance of tau. Actually, we should take the square root. And then after you square it, it becomes squared. The top part also squared, the bottom part, it becomes variance. So this is the expression for the square, the correlation between x and the tau. And then just by using the formula of the x, observe the x here. So we have alpha tau plus e. So you can just do the derivation covariance between x and tau. Okay, x is alpha times tau plus e. So you do the derivation, it becomes a covariance. Actually, we have alpha, okay. So here we have alpha. So alpha variance of this tau, okay. So here it's just alpha variance of tau, but you just needed to square it because there's a square. Okay, squared this number, squared this number. So that's the top part. And then the bottom part is the same. And now you have this variance of tau on the top part and the bottom part. Cancel one term, okay? Cancel one term. We have the squared canceled, so we only have one. Now let's look at this part. This part. We have variance of tau over variance of x. And we have the alpha. Okay, so based on the formula, we have alpha. So that is just the reliability. Oh, so messy. That is just the reliability of this x, because x is alpha times tau plus e. Okay. So this is the reliability of x if we consider the alpha reliability. So the reliability here is a squared correlation between the observed score x and the true score tau. Okay, we just proved that part. Good. Okay, we have already covered this, and actually this is the review slides. Think about the R squared. So this is a slide from my regression course, the other foundation course. When we mention the R squared, we have SS regression, SS total, the ratio is R squared. Look at this part, it's kind of like a reliability. It's kind of like, okay, variance due to the true score here. Here, this is a model part, this is a total variance, and then this is R squared. So this is R, okay, you can think about this is the correlation between the observed score and the true score. Squared, this is kind of reliability, okay? Of course, this is a very simple case in regression, but in SEM, we needed to consider more about the residual part, measurement error part, so that's why I make it so complicated. Now, let's look at some empirical ways to estimate our reliability. So we just talk about the definition, we talk about different types. So how to measure that one, okay? So we have different empirical ways to get the estimate. The first method, of course, we have more, but these four are very, very popular, okay? Test, retest. Basically, we have some, okay, you can think about just one test, okay? And then we do it again. Different time points, t times t and t plus 1. Do the correlation. And then alternative forms. So we have, actually, let's look at the test and retest first. Okay, so because we have some advantages for test and retest, for example, memory effect. When you do the second time, the true score actually cannot measure the true score. It's different. So we can have alternative forms, and also alternative forms has some limitations or disadvantage. Then we can have split half, and then we can have Cranbach alpha. So let's look at the test and the retest. So it's 209. Yeah, it's here. Okay. So there are number of ways to estimate the reliability, and we're gonna cover these four parts: test, retest, alternative, and the split half Cranbach alpha. Okay, this is a test retest method. So basically, you just test twice. Okay, the time t, we have the measure at time t. the observed value is xt, and we have alpha t, tau t, and et. The second time, okay, t plus 1, that's different time points. We have second measure, xt plus 1, and we have alpha, and we have tau, we have e. So these are different time points, the first and the second time points. And of course, we have a lot of assumptions. Okay, we'll assume the expectation of these two measurement parts is 0. Okay, and these two are uncorrelated. And then we can have the test retest. We put a lot of assumptions here. Okay. And then after we got that scores, we just calculate the correlation between the original observed score and the second time observed score. Just calculate the correlation, okay, correlation between xt and xt plus 1. So we finally have the reliability. That is one way empirically to do the test of the estimate. But we do have some, yeah, as I mentioned, we have a lot of assumptions here. So we have some limitations, okay? So just tell us we have some limitations. In this case, we assume that actually the test and the retest have the parallel form, parallel measures. So that's why we have the reliability calculated. Yeah, we assume that the correlation of any two parallel measures equal their reliability, since all parallel measures have identical reliabilities. Okay. But is that very good method? Actually, it's no. Okay, so we have a lot of limitations. So for example, okay, the true score may change over time. We assume that T1, T2, T1 and T2, 2 time points, we have all exactly the same, but actually they may be different. Okay. And also the activities may not be the same when you have different time points exact test. And also memory effects, okay, it gonna violate the assumptions of the test retest form. Yeah, if you want, you can just read through these paragraphs. Okay. So we have a lot of factors gonna influence the assumption.
So a lot of your highlighted selections we could use for our
Yeah.
answers.
Yeah. I
Okay.
just want to give you some hint. Yeah. So, yeah. And also the covariance between time point 1, time point 2, two measurement errors. Okay, we assume that these two covariants are the same, but in reality, think about that. Time measurement error at time point 1, measurement error at time point 2 may be highly correlated. So these assumptions also may be violated. And of course, we have this assumption, okay, the variance of ET and variance of E plus T1 should be the same. Also, it could be question solved. Then, due to a lot of limitations for the first method, we have alternative forms. Okay, alternative forms. So that means these two tests are not exactly the same. For the first method, they are exactly the same test. We just do it twice. And alternative forms, we have form A, form B. Think about the test in our, actually we have a lot of projects. Okay, we're trying to develop two forms, form A and form B, and the kids are sitting next to each other, cannot have any, the same answers. So in that case, we still have, these two measures, X1 and X2. So, and we also collect different time points, but we assume that these tau are the same because alternative forms, we assume these are measures the same variables, same trait. But several of the limits of the test and retest are still true for the alternative forms. Okay, so we cannot just improve that a lot. But we do have some advantages, okay, for alternative forms. if we're gonna compare it with test and retest, because there's a no memory effect, because these are different tests. So there's no memory effect. And we also have the errors, okay, measurement errors for one indicators are less likely to correlate with the new measure because they're different. But because we have some other limitations, people trying to use another method called split halves. So basically we have a bunch of items here and we're trying to split equally. So part one, part two. And then we got the measure from part one, we got the measure from part two, and then calculate the correlation. Yeah, this is another way to get the reliability of that test. So in that case, we have x1 and x2, okay, two parts. And they are from the same, they are measured the same tau. So that's why we have tau one here exactly the same. Although the measurement errors are not the same, but it's different. So we assume these are exactly the same tau, measure the same tau here. And we have still needed to assume these assumptions, okay? All of these are our assumptions. Okay? And then same thing, okay, we're trying to get the correlation between x1 and x2, okay, correlation between x1 and x2. So this is the covariance between these two measures, the variance part, the square root. And then, actually, if you look at the equations of tau1, x1, x2, you can just simplify the top part by this one, okay, because the E1 and E2 are incorrelated. So we have the covariance part 0, and the tau and E are independent, so we only have the variance part left, so variance of tau. And also these two, we'll assume that x1 and x2 measure the same tau, so we have this part. So this is our reliability of the x. Now let's look at a very important equation. So for split half, we have a Spearman-Brown proxy formula. This is very famous. Okay, maybe the Cronbach's alpha is the most famous formula. This is the second popular formula. Okay, Spearman-Brown proxy formula. So what is this? This tells us, okay, so we have the correlation, okay, we have the tau because x1 and x2 measure the same tau. So we have the tau and the sum score, split half. We got the sum score of these two measures. And then squared correlation, kind of like this is starting point, okay? So we start from this correlation. So we have tau, just based on the formula, the definition of the correlation, okay? Covariance between tau and the sum of x1, x2, and then squared. So bottom part, variance of this one, variance of this one. And then you do the derivation. Okay, so x1, x2, we have formula for split half. x1, x2 are for function of tau. Okay, here, just use the formula here. And we replace the x1, x2 here and do the derivation. So finally, so we have tau1. Okay, so we have tau1 here. We have E1, E2 here. We just divided the other part squared. So originally we have 2. So squared we have 4. 4 and the variance of tau. So this is the tau part from here to here. And then the bottom part, okay, variance of tau1, just copy this term. Variance of this sum of the x1 and x2 split half because we're trying to get the sum scores. So variance of the first half, variance of the second half, covariance between these two halves, okay? They are covariance because these two are highly correlated. They measure the same tau. And then from here to here, you needed to do more calculation. Okay, so we assume that x1 and x2 are measuring the same thing, and the residual part, the variance part, has the same variance. Okay, variance of E1, variance E2 is the same, then we have this new formula. Okay, so from here to here, from here to here. So from here to here, it's very natural. So we got this part. And from here to here, you can just combine these two forms. Okay, so here we have variance 1, and here we have variance 2. But if you do the replacement of x1 and x2, okay, x2 is tau 1 plus e2. Okay, x1 is tau 1 plus e1. And the variance of this part is the same. So actually, this is a variance of x1. Okay, it's the same thing. And the variance part is the same. You assume that. So this is variance 1. So we can just combine them together. So we have 2 variance of x1. And here we have 2. Okay, so we combine the 2 here. So we combine the 2, and then 2 is gone, and here becomes 2. And here we have tau 1. Okay, tau 1. So we cancel the tau 1 here, cancel variance of tau 1 here. And we have this part. Okay, both part divided by the variance of x. So we just divide variance of x on the top part and the bottom part. So the top part becomes 2. Okay, variance of the tau divided by variance of x1. The bottom part, because it's the same thing. Okay, so now we have already canceled this part. So it's here it becomes a variance of tau. Okay, so now we have variance of tau. Okay, divided by the variance of x1. Okay, and here we have x1. Okay, variance of x1 divided by x1. So this is equals 1. So finally we have this form. Okay, so let's look at this form. This is variance of tau over variance of x1. So this is a reliability. Okay, so 2 times the reliability over 1. This is 1. Okay, this is 1. This is 6. 1 plus this is another reliability. This is the reliability variance of tau over the variance of x. So this formula. Okay, so this formula. 2 times the reliability of x1, x2 over 1 plus the reliability of x1, x2. X1, sorry, just x1. Is the squared correlation between 2 score tau and the sum of these 2 observed scores. So this formula is called Spearman-Brown's proxy formula. Okay. And we also talk about these the advantages. Okay, so 1, 2, 3. So because for split half, we don't need to assume the perfect stability of tau at different times. We can have stable assumptions. Okay, memory effect. There's no memory effect because split half, it's different. And the correlated errors are not like a test retest. And also practical advantage that it's often cheaper. Okay, if you think about the budget, the cost, okay, it's often cheaper and more easily obtained than over time. But they do have some advantages, okay? Because we have assumed these are parallel measures. All of these assumptions we derived here, derived on the board, assume that these are parallel measures. So that's why we can have really good formulas like this. Okay. But in reality, it's not so easy to get the parallel measures. And then we can have Cronbach's alpha coefficient. So finally, people have this case. So let's look at this. This is a derivation. So let's just look at the slides. Yes, split half, Spearman's proxy. This is a detailed derivation. And then people have, the researchers developed the Cronbach's alpha. Okay, it's the most popular reliability coefficient in social and behavioral research. So what is what is that formula? Okay, it just measures the reliability of a simple sum of tau equivalent or parallel measures. Again, we assume that each item actually is tau equivalent or parallel measures. And then we're gonna just get the sum and measure the reliability of that sum. Okay, so what's the formula? So this is the formula. Okay, finally we have this formula. This is the derivation. So let's just look at this formula. So what does that mean? Suppose there's the whole test has Q items. Q is number of items. For example, I have 10 items. So Q here is 10. So Q over Q minus 1. Okay, this is a constant coefficient for the formula. And then what is this? Okay, 1 minus, what is that? The bottom, let's look at the bottom part, variance of the H. What is H? H is the sum score of 10 items. So I have item 1, item 2, each item I have score, so get the sum score. So that is a variance of the sum score. This is the bottom part. So what is the top part? It's a sum. Okay, this kappa sigma sum of 1 plus 1 equals 1 to Q. 10 items. For each item, what is the variance? Okay, this xi is each item. 10 items. For each item, what is the variance? That gets the sum of each variance over the variance of the sum score. Okay, 1 minus this ratio and the time this constant is the reliability. But why do we have this Crumbus alpha? Why do we have this complicated form? It started from here, okay? Started from, this is a reliability is a correlation, the squared correlation of the true score of the sum score H here. This is the sum score. You just think about the reliability of the squared half, okay? So again, it started from the definition, okay? Squared correlation, okay, squared the variance, covariance between the tau, the true score, and the sum score, and the variance of the true score tau, okay, the variance of the sum score. And then the H, okay, the H, this is H, this is the sum of all Q items, x1 plus x2 to xq. This is H. And this is just explanation of the previous form, okay, tau the true score, and the square, okay, variance part. Now, next step, from here to here, we're trying to expand this form, okay, covariance between tau and all of these items, 10 items. So we have Q items. So actually, we have Q tau, because all of these measures are parallel or tau equivalent. They are measures the same tau, okay? So we have Q tau, okay? Each X is tau plus the measurement error part. So the Q times the true score tau plus the residual part, okay, the sum of the residual, I from 1 to Q, and all of this EI, measurement error from 1 to Q. That's from here to here. And then from here to here, by using a lot of assumptions, because we assume, okay, the variance, the expectation of the measurement error is 0, okay? So we have Q, so we just take it out with Q squared actually, okay? And the covariance of tau and each tau and the E are independent, so there's no covariance. So finally, we have the Q times, okay, take it out of Q and the variance of tau and squared, okay, and squared. So this is from here to here, this is a new step. We copy the bottom part. And the Q, we take it out, okay, Q squared. This is a variance of tau, okay? And we can cancel the one variance of tau, because here we have 1, here we have squared. So that's it. But from here to here, we need to use some tricks, okay? In order to get the Crumbus alpha from here to here, we use the tricks like here, okay? From bottom part and the top part, we times Q minus 1 at the same time, okay? It doesn't change anything, but we just times the Q minus 1. And also Q squared equals Q times Q, okay? So everything keeps the same Q. And then we keep this ratio out, okay? So we have this ratio. And inside, okay, we have this part, we have Q squared, and minus Q, we have this part. this is another trick from here to here. We add something, we minus something. Okay, this is the same term. We add something, minus something, we can cancel it. But by adding this term, when we look at this part, okay, so what is this? The q squared, the variance of the true square, and plus sum of two of the variance of the residual part. It's just the variance of the sum score of all x. Okay, think about this case and this case, it's exactly the same. So q squared, variance of tau, is a true score part. And as a residual variance, we have the sum. Okay, add them together, it's just the variance of the sum score here. And the minus, we have this part. Okay, we can also combine these two parts. Okay, q, the variance of tau, and plus, because we take out the minus part. This is a sum of variance of e part. And we have the same bottom part. And from here to here, we just simplify. Okay, so variance of h cancel. It's 1. 1 minus. And this part, okay. This part, combine these two. Okay, this is the true score. This is error. Okay, so we have q variance of the true score. Here we have sum of variance of residual part. This is also the sum of the variance of the item I. Okay, because each observed item xi is a combination of the tau and the e. So this is just the sum of the variance of the item xi. So that's why we have this formula plus alpha from here to here. Okay. So it looks weird, but actually we also have some popular forms, general form, just like this. From the alpha is calculated. Here we use different notation. Okay, suppose we have j items. In the previous slide, we have q items. It's the same thing. J items, j over j minus 1. This is a constant coefficient here. And then what is this? Okay, you can look at this. Okay, this is kind of like a covariance between the x and x, the sum of the covariance terms without, okay, so the sum of covariances of this matrix, okay, by using these conditions, and j and ji are not the same. So the diagonal part is not calculated. So when j and ji is the same, it means the diagonal part is not calculated. We just get the covariance elements of all other off-diagonal parts. That's the sum. And this is a sum of all elements, okay? Or you can use the average, okay? This is average of all off-diagonal elements. And get the sum. So this is a more general form, but the meaning is the same. Okay, this form and this form, meaning same because here we have the item. Okay, each item, like xi, h is the sum of all parallel terms items here. That's how we have the carbon alpha. Okay, so that's a formula. That's a formula. So if you go to the page 215, it just gives us the details of the derivation. So H is the sum score of all items, and we just started from the square correlation between the two squares and the sum score. The sum of the observed score, and we use a definition, do the derivation, and of course use some tricks. Okay, here we have some tricks. And finally, we have the formula. So there's assumption, again, there's assumption. Okay, so this derivation holds for either parallel or tau equivalent measures. Okay, so we have to assume that all these items are measured the same tau. That's why we can do the derivation like this. Okay, so item 1, 2, 3, 4, item Q. Okay, in total Q items, we have the same trait, same tau score. Okay. And of course, for your homework, you don't need to cover this part. Okay, you don't need to show these details. You can just say that, okay, we have the Crumbler alpha is one method to measure, to estimate the reliability. And it derived based on this formula. Okay, the sum score is, okay, all of this measurement, tau equivalent or parallel measures sum. Okay. Yeah, this is the journey. And we have some examples in the textbook. Yeah, this is another case, the congeneric form. Okay, so if you have the congeneric forms, you can have alpha instead of just the direct tau. Okay. And same thing. Okay, so that's it. That's for our Crumbler's alpha. And the next part we talk about the alternatives to classical reliability measures. So previously we just used classical tensor theory. Okay, so we have these equations. But actually for SEM, after we learn the factor models, we can have this more complicated form than the classical tensor theory. We can have the factor loading matrix here. This is the true score factors. Okay, we have lambda matrix. So it's different story, but actually the logic is the same. We're trying to get the variance of the true score, the true scores here, and the variance of the observed score and get the ratio. But the way to get the variance of true score is kind of like different. Okay. So SEM-based reliability is more accurate than the classical Crumbler alpha. Okay, so suppose this is a factor model. Yeah, next time we will just cover this part. Factor model, we have different factor loadings, we have different factors, and we're trying to get the true score. This is the true score, okay, of this measure y x here. This is the true score of the variance of the raw score. The ratio is reliability, okay. And if we have one factor model here, we have n factor, okay, n factors, assume we have n factor. You have one factor model. There's another popular reliability called omega. Okay, coefficient omega. Actually, that based on the factor model, but it's one factor. So we have the lambda coefficient here, and there's a residual part, the variance part. So this is the formula for omega. So all of these are alternative reliability estimates. Okay. So these are more accurate than the traditional Crumbler's alpha. Okay, I think I have already covered the chapter 6. Yeah, so. And the last slide about the relationship among validity and the reliability. I think we have already covered this part. So that's it. That's for today's class. And you also, yeah, so you needed to finish homework 1. So basically 3 parts. About validity, just tells about the definition or types and the different methods and some limitations. Reliability, what's the reliability? Okay, different types and the different empirical methods to measure it, formulas, equations. For equations, you can give me the Crumbler alpha's formula because that is really important. Crumbler's alpha formula. That's it. Okay. And you can talk about different types of measures. Tau equivalent, or starting from parallel measures and the tau equivalent and the congeneric. That's it. Okay. And also the difference between the validity and the reliability and the relation. 2 points. That's it. Any question? Yeah, you can just read the chapter 6. It gives you all the details of these concepts. And it's due next class. That's all for today's class. Okay, any question? Good, okay. Next time, we are going to formally move forward to factor analysis. And we're gonna compare that with principal component analysis. Factor analysis and the principal component analysis are very confusing. So people just think about, okay, maybe principal component is just factor analysis. Factor analysis just, no, they are different, okay. But they are quite similar, but they are different, okay. And we have EFA, CFA, higher order factor models. Yeah, we have a lot of it. Model identification.
Thank you, ma'am.
Good. That's all for today's class. Yeah, thank you.
You asked them how much when my wife sells them at the daycare, she sells them for $4 a dozen. If you wanted to, that's okay. You want them free, I don't give a shit. But if you felt implied, it's up to you.